Shear in beams. This model was designed to help students understand how shear stresses arise in beams, why those stresses vary from place to place over a beam cross section, and why they produce specific shear flow patterns. To provide context for the model, you imagine this that is a part of cantilever beam like this one. If that were the case, the bending moment acting on the model at section B would be larger than that acting at section A. We represent the tensile bending stresses that these moments using red arrows overlaid on plexiglass box and the compressive ones with blue arrows overlaid on the beam. You can see the bending stresses at B are also larger than those at A, as we will discover shortly. Differences in bending stresses from one section to another along the length of a beam are the reason that shear stresses arises. Before we begin that discussion, however, notice that the length of each arrow is proportional to the magnitude of the stress that represents. As a result, the volume of each plexiglass blocks is proportional to the force generated over its base area. As can see, large forces are generated in the flanges and smaller on the web. Not only that, but the flange forces are relatively far from the neutral axis of the beam, and so they contribute much to the bending moment. The forces on the beam are much smaller and they act as shorter moment. As a result, they contribute relatively little to the moment. To understand how shear stresses arise in a beam, imagine that we used a saw separate on one fiber of the flange from the rest of the beam. As you can see, the force from the bending stresses on end B of the fiber is larger than that produced at end A. In the worked example included at the end of this video, the difference in these forces is 15 units. So far, this fiber to remain in equilibrium, the rest of the beam must exert a force of 15 units on it. We treat the fiber as it were a free body and therefore draw the arrow on the fiber in the direction of force that exerts on it. At the same time that the beam is exerting a force of 15 units on the fiber is exerting an equal and opposite force on the rest of the beam, as shown this arrow. This is the top view of the beam. The forces between the fiber and the rest of the beam act parallel to the cut. So we call them shear forces and we represent them using arrows, and they have a single-sided head. In contrast, forces that act normal to the surface like this produced by these bending stresses are called normal loads and represent them using arrows that have symmetrical heads. If we know, imagine a cut that removes two fibers of the flange, that pair will be out of balance in the axial force by twice as much as a single fiber we originally considered. So to keep this new free body diagram in equilibrium, a shear force of 30 units must act, as shown by these arrows. If we cut off all 5 of the fibers that make up the top flange from the rest of the beam, the total axial imbalance is 5 times 15 or 75 units. And that is the magnitude of the shear force that must act on the newly cut surface that is between them and the rest of the beam. A fiber closer to the neutral axis of the beam experiences bending stresses that are smaller. The difference between the forces on the two ends of this fiber is only 9 force units. Adding 9 to 75 will gives you the total shear force of 84 units. The difference in the end forces, the fiber just above the neutral axis, is only 3 units. Adding that to 84 will give you 87 units. Tension and compression, the fibers between the neutral axis carry rather than tension and compression. As a result, those fibers are out of balance in the opposite axial direction compared to those above it. If we imagine a cut below the neutral axis, some of these fibers are now included, and they reduce the total axial imbalance compared to beam cut right at the neutral axis. That is why the maximum shear force is always found at the neutral axis. Notice that these shear forces arise because the bending stresses and the moment that cause them vary with position along the length of the beam. It is customary to report the shear stresses on the beam across the section rather than the shear forces. For the sake of simplicity, the web and flanges in these models are assumed to be of unit thickness. Also, the two cross sections are considered to be separated by a unit amount. Even though the physical dimensions of the model may suggest otherwise, as a result of these dimensional choices, the shear stress along any one of the cuts will be numerically equal to the shear force it carries. Notice that our cuts always go across the thickness of web or flanges. That's why all of the points in the cut are very near to the axis and would generally be expected to carry and would generally never the cut flange parallel to its top surface. For example, points along such a cut would be relatively distant from the various stresses. Various points along the cut could differ substantially. One can plot the magnitude of the shear forces as a function of the distance between the cut and the outer extremity of the flange. As you can see, the graph is linear, a result confirmed by the calculations shown on the right. Similar graphs can be made for other regions of the flanges, and by convention, the axes are typically oriented as shown here. As these calculations show, the shear stress in the web takes a parabolic form. Shear stress distributions plotting all of these graphs on a single figure reveals what is called the shear stress distribution for that cross section. In order to understand shear flow, we must transfer the shear stresses we just calculated from their respective longitudinal cutting planes to the beam cross section. We do that using the simple fact shear in plane always involve 4 matched stresses with arrows that go head to head. If we concentrate on this inside corner of the flange fiber, the shear on the cross section must go tail to tail with the longitudinal stress arrow, and so it must point outwards and its magnitude must be 15. If we focused on the outside corner of the adjacent flange fiber, we would get exactly the same result. We can show the shear stress on the cross section using a single-sided arrow. At 2 fibers in the shear stress is 30, and so that is the shear stress shown on the cross section at that location. To analyze the web, we note that its shear operates in a vertical plane. Unlike that in the flanges, which operates in the horizontal plane, collectively those shear arrows show, however, the shear flows across over the section, and that reveal what is known as shear flow. These arrows represents forces or stresses that must act on the beam for it to remain equilibrium. So clearly an upward force on the end of the beam that carries a larger bending moment, and a downwards force must act on the either end. If we examine the beam from which these models was taken, you can see that those shear directions are indeed correct. Not only that, but if we estimate the total vertical load on the beam, the summing indication that vertical forces we get 405 units. In value quite close to the shear of 412 units. Noted in the worked example that follows the credits. It may seem surprising that the shear forces acting on a beam could be determined solely from the bending stresses acting on 2 nearby cross sections. However, the differences between the stresses on those 2 sections are a direct result of the changes in the bending moment M with axial position X, and that rate of change can be used to calculate the beam shear by using the well-known formula V is equal to dm by dx. This relationship explains mathematically why shear and changes in bending moment are closely related. Hope this video helped you to understand how shear stresses arises in the beam.